Okay, so that's a little bit about sampling. Does it make sense?
Yeah.
Good. If it doesn't make sense, you must please interrupt me. Okay. The next thing we need to think about when we do our sampling is what we are actually measuring and how we are measuring it. Now, there are two basic variables. A variable can be discontinuous or it can be continuous. If I want to measure how many people are taller than 6 foot in this room, it's a discontinuous variable because it has to be 5, 6, 7. It can't be 7.5 people. Some people are very short. They look like a half person, but they are a person. Okay. So it is a discontinuous variable. Right. When I measure the lengths of people in this room, it is a continuous variable. You can be 6 foot, you can be 6'1", you can be 6'2", whatever the case may be. You can be 6 foot 1.758 inches, right? It's continuous. Theoretically, you can have an infinite number of decimals to make it continuous. So something like plant length is a continuous variable. Plant mass is a continuous variable. But the number of albino plants in a field is discontinuous. Now that will become important later. The one thing I want to emphasize, and I don't want to spend too much time on this, is that very often in science or in breeding or whatever we're doing, we use different kinds of measurements. We might have a nominal scale, where we just put things into categories, susceptible, moderate, and whatever the case may be. We have an ordinal scale, where we put things into some kind of order. Okay. We have an interval scale like degrees Celsius. You've got between 1, 2, 2 to 3, that's an interval. What we generally want to do if we're going to use statistics is to use what we call a ratio scale. A ratio scale is something that includes an absolute zero. Now people say to me, but temperature includes an absolute zero. It does not, okay? We talk about 0 degrees Celsius, but that is relative to something, and generally it's the freezing point of water. You can have negative temperature, anything below 0. You can have something that's higher than 0. Okay? It is an interval scale, it is not a ratio scale. 10 degrees centigrade is not half the temperature of 20 degrees centigrade, because you're not working to a relative or an absolute 0. If I say that I have no people in this room, I can't have a negative amount of people in this room. I have an absolute 0. So generally, when we use statistics and we're going to measure something that we want to do a statistical analysis on, we need to use what we call a ratio scale. You are 3 foot tall. Now you're a little bit taller, but he is 6 foot tall. You are half as tall as he is. I can express it as a ratio. Okay, you are 50% shorter than he is, or he is, it's a ratio. Okay, and generally in statistics, we work on ratio scales. So something like an absolute number, you're 6 foot or 1.3 meters or whatever the case may be, we can reference that to 0. We can also express the ratio scale as a percentage. As I've just said, you 50% of his length. Okay, and that is very essential when it comes to doing statistical analyses. So we need to be careful how we measure and what we measure to make sure that it is something that can, or that we can apply statistical analyses to those measurements. Now, unfortunately, I noticed that even in a journal like Plant Disease, they use a straightforward analysis of variance on disease ratings, which is strictly speaking incorrect. Okay, because generally when I rate a plant and I give it a 1 rating and I give that a 2 rating and I give that a 3 rating, we're generally on a log scale more than, and very often it's more an order than it is an actual value. Now I know the jury's out on that one, but we have parametric and non-parametric statistics, and I don't want to go there. So we just need to be careful that what we're measuring is correct. Okay, so plant length is a ratio scale. A plant of 150 millimeters is 3 times 1 of 50 millimeters. I can express them as ratios. Okay. The other thing that we want to be careful of is that when we go and measure, we are precise and we are accurate. And we need to be aware of error. When an observation is made of a discrete variable, for example a count, we're pretty sure it is precise. There are I did a count earlier, there are 32 people in this room. Okay, I can do that fairly accurately. When it comes to a discontinuous variable, we need to be aware that we can pick up error. So I'm going to go and measure the heights of wheat plants, and I take a measuring stick, and the measuring stick has got 10 centimeter intervals on it. I am only precise to the nearest 10 centimeters. Okay. If I take a measuring stick and it's got 1 centimeter intervals, I can be precise to the nearest 1 centimeter. You'll never get close to the exact figure. You never get to absolute numbers, but you can get pretty close. Now, what does this mean in practice? I'm going to go and measure plant heights. And the plant heights vary between 150 and 200 centimeters. Generally, I want to divide that range into anything between 30 and 300 steps. So the plant varies from 150 to 200 centimeters. In other words, the range is 50 centimeters. If I use a 1 centimeter scale with my measuring stick, and I use 50 steps, it's precise enough because an error of 1 unit, in other words, an error of 1 centimeter, only represents a 2% error. If I take my measuring stick with a 10 centimeter gap, I've only got 5 steps. It's not precise enough because an error of 1 unit represents 20% error. Okay? So when you're measuring, be aware of the range you're measuring, be aware of the units you're using, okay, because you can build in error. And error very often becomes multiplicative. You start here with a 10% error, and then the next step you do another 10% error, and eventually you have a huge amount of error. So you want to be careful that you are accurate and that you are precise. A note on precision and accuracy. An expensive laboratory balance may be precise to the second decimal place, but if it's badly calibrated, it won't be accurate. So it will be doing precise measurements but giving you the wrong value. A broken clock is accurate twice a day. Okay? Right. So there's a difference between accuracy and precision. And we need to make sure that we know what we are measuring, why we are measuring, and ensure that error and bias and random sampling and everything else is correct. Okay, so now I've gone into the field and I want to measure the length of those plants I was talking about. And I measure the length to 100 plants and I put them in a table like this. And what have I got? I've got a jumble of figures. Right. They mean nothing. And now we're starting to move into statistics. The aim of statistics or biometry, or whatever you want to call it, is to take these numbers and make some kind of sense out of it that everybody can understand, and that gives me an idea of what is going on in the population that I want to measure. So now I've got all these figures. One of the things that I can do with this is I can divide those figures into what we call frequency classes. So I can look at the range of those figures and I can decide I'm going to divide them into 20 classes, 10 classes, whatever the case may be. Okay, so I'll then divide these into classes and I'll work out how many plants fall into each class. Okay, so 74 centimeters is a frequency class, and I decide that on either side of that I'm going to go half a centimeter, and all the lengths between 73.5 and 74.5 I will put into the 74 centimeter class. Okay, and I then put all these numbers into a table, and essentially I'll end up with something like this. There's the frequency class, there's the midpoint, which we call the class frequency, and in here I have the number that goes into each one of those classes. And I can put that on a graph, and immediately those numbers start taking shape. You can see two things there. You can see that the classes at the extreme have very few numbers, and the ones in the middle tend to have a greater number. You can now start making some kind of sense out of what is going on in those samples and in the population. I mean, you can immediately get the idea there's some small plants, there's some tall plants, and okay, there's quite a wide distribution. The class intervals don't have to be a single unit. They can include a number of units, like 155.5 to 158.5, and so forth. The class frequency is the midpoint, and ideally there should not be less than 10 classes and not more than 20, because otherwise you're going to have so many classes and so many peaks, you're not going to know what's going on. Okay, that can then give you an idea of what's going on, and we can present it in the form of a histogram. We can present it in the form of a frequency curve or a pie chart. And immediately you can see that the greater percentage here, 20 of them fall into that category, and you can then go and get some picture of what's going on in your population.